Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Take a moment to settle in, to let the day begin to fall away. Get comfortable. Let your breathing slow. There's nowhere you need to be right now except right here. Where in the world are you watching from tonight? A quiet room where the stars might be visible through your window. A cozy space where the universe feels both impossibly far and somehow, after tonight, just a little bit closer. Tonight, we're going to explore one of the most remarkable discoveries in recent astronomical history. The James Webb Space Telescope, humanity's newest and most powerful eye on the cosmos, has found water on a planet just 26 light-years away. 26 light-years might sound like an impossible distance, and in many ways it is. But in the vast scale of our galaxy, it's practically next door. More importantly, it's a distance we could theoretically one day reach. We'll discover what this planet might be like, understand how we detected water across such vast distances, contemplate what this means for the search for life beyond Earth, and gently explore the beautiful, impossible dream of one day travelling there ourselves. But don't worry. This isn't going to be a frantic race through technical jargon or a breathless countdown to some revelation. Instead, we'll move slowly and carefully through this discovery, taking our time with the science, the wonder, and the profound questions it raises. By the end, I think you'll look at the night sky a little differently, knowing that among those distant points of light there's a world with water, waiting. If you enjoy these calm explorations of the cosmos, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, journey after journey into the universe. So settle in. Let your shoulders drop away from your ears, take a slow breath in and let it out even slower. And let's begin our slow drift toward a world 26 light-years away, where water exists beneath an alien sun. There's no rush. Nothing you need to remember or study. Just listen and let the story of this distant ocean world unfold at its own gentle pace. The discovery came through as data, not as a photograph, not as a dramatic image, but as lines on a graph, peaks and valleys in a spectrum of light that had travelled for 26 years to reach us. To the trained eye, those lines told a story that humanity has been hoping to read for decades. They said, water. They said, another world. They said, you're not looking at a barren rock, but a planet with an atmosphere, with chemistry, with the fundamental ingredient we associate with life itself. The James Webb Space Telescope made this detection in 2023, though we're still analysing and confirming the full implications of what it found. The planet is designated as an exoplanet orbiting a red dwarf star, and while the exact catalogue designation matters less than what it represents, astronomers have been carefully studying this world with increasing excitement. What matters is this: 26 light-years away, a distance that represents about 153 trillion miles, there is a planet roughly the size of Earth, and in its atmosphere we've detected the spectroscopic signature of water vapour. This might not sound revolutionary at first. We've detected water elsewhere in the universe. We know it exists on moons in our own solar system, frozen beneath Europa's ice, liquid beneath Enceladus's southern pole. We found it in the atmospheres of gas giants orbiting other stars. But this is different. This is a rocky planet, potentially in the habitable zone of its star, at a distance from us that, while vast by human standards, is close by galactic measures. This is a world we could, with technology we can actually envision, potentially reach within a human timescale. The detection itself required everything the James Webb Space Telescope was built to do. Positioned 1 million miles from Earth at what's called the second Lagrange point, Webb used its massive mirror, 6.5 metres across, made of 18 hexagonal segments of gold-coated beryllium, to collect the faint infrared light from this distant star system. When the planet passed in front of its star from our perspective, blocking a tiny fraction of the star's light. Webb didn't just measure the dimming. It measured how that light changed as it filtered through the planet's atmosphere. And in that filtered light, in the specific wavelengths that were absorbed or transmitted, the telescope found the fingerprints of water molecules. H2O, that simple combination of hydrogen and oxygen that makes up our oceans, our bodies, our world. The same molecule, the same substance, existing in an atmosphere 246 trillion miles away. Revealed to us by light that left that world in 1997, the year some of us were born, the year before Google was founded, light that has been travelling through absolute darkness and emptiness for longer than some people watching this have been alive. The discovery was confirmed through multiple observations, verified by different instruments aboard Webb, cross-referenced against known spectroscopic signatures. This wasn't a maybe or a possibly. This was as certain as astronomy gets when working with such faint signals across such distances. Water exists there, and that changes everything about how we think about this particular pale dot among the countless stars. Which brings us to perhaps the most remarkable part of this story, the distance itself and what it means for the future of human exploration. 26 light years. Let's sit with that number for a moment and truly understand what it means, both as a measure of cosmic distance and as a measure of possibility. A light year is the distance light travels in 1 year. Light moves at approximately 186,000 miles per second. In 1 second, light could circle Earth 7.5 times. In 1 year, travelling at that incomprehensible speed without ever slowing down, light covers about 5.8 trillion miles. That's 1 light year. Now multiply that by 26, and you have the distance to this water world, roughly 153 trillion miles. If you tried to drive there in a car travelling at highway speeds, it would take you more than 170 million years. But here's what makes this distance so significant. In the context of our galaxy, 26 light-years is nothing. The Milky Way is approximately 100,000 light-years across. The nearest star to our Sun, Proxima Centauri, is 4.2 light-years away. The centre of our galaxy is about 26,000 light-years distant. By those standards, this planet is in our immediate neighbourhood. It's in what astronomers call the local interstellar neighbourhood. The small bubble of space within which we might, one day, actually be able to send probes or perhaps even humans. To put this in perspective, imagine the galaxy as the United States. If you're in New York, Proxima Centauri is like New Jersey right next door. This water world 26 light-years away is maybe like Pennsylvania or Maryland. Still very much local, still part of the general area, definitely not California or Alaska. It's close enough that we can study it in detail, close enough that the light we're seeing is relatively recent by cosmic standards, close enough that it exists within the realm of realistic future exploration. The Voyager 1 probe, launched in 1977, is currently the most distant human-made object, having just recently entered interstellar space. It's travelling at about 38,000 miles per hour relative to the Sun. At that speed, it would take Voyager approximately 460,000 years to travel 26 light-years. Clearly, our current technology isn't fast enough, but that's with technology from the 1970s, powered by nuclear generators that were cutting edge half a century ago. What makes this distance potentially reachable is that we can actually conceive of technology that could travel much faster. Theoretical spacecraft using laser propulsion, like the Breakthrough Starshot initiative proposes, could potentially reach speeds of 15 to 20% the speed of light. At those velocities, you could reach this world in 130 to 170 years, still longer than a human lifetime, but within the span of a few generations. You could launch a mission, and your great-great-great-grandchildren could receive the data. The civilization that sent the probe would still exist when it arrived. This is what makes 26 light-years so tantalizingly close. It's at the edge of what we might actually reach, not in our lifetimes perhaps, but in the lifetime of our species. It's distant enough to be a tremendous challenge, but close enough to be a realistic goal. It transforms this discovery from merely interesting to genuinely meaningful for humanity's future. And there's something profound about the fact that the light we're seeing from this planet left there in 1997. When that light began its journey, many of us were children, or not yet born. The world was different. We had no idea the James Webb Space Telescope would even exist. And yet that light kept travelling, crossing the vast emptiness between the stars, carrying with it the story of a distant world, until it finally reached our golden mirror in space and told us, there is water here. Let's contemplate what that water world needed to reveal itself to us, the telescope that could see it, and the technology that made Webb possible. The James Webb Space Telescope is, without exaggeration, one of humanity's greatest achievements. It represents decades of planning, billions of dollars of investment, contributions from thousands of scientists and engineers across multiple countries, and a level of precision engineering that pushes against the very limits of what we can build. Webb launched on Christmas Day, 2021, aboard an Ariane 5 rocket from French Guiana. The launch itself was just the beginning of an impossibly delicate deployment process. The telescope was too large to fit in any rocket, so it had to be folded up like the most expensive origami in history, then carefully unfold itself in space over the course of 2 weeks. Engineers had identified something like 344 single points of failure, any one of which could have ended the mission. Every single one had to work perfectly, and somehow, impossibly, they all did. The telescope's primary mirror is composed of 18 hexagonal segments, each precisely shaped and positioned to function as a single, perfect mirror 6.5 meters across. That's about 21 feet, making it nearly 3 times larger than the Hubble Space Telescope's mirror. Each segment is made of beryllium, chosen because it's both lightweight and maintains its shape even at the extremely cold temperatures where Webb operates. Each segment is coated with a microscopically thin layer of gold, approximately 1,000 atoms thick, because gold is the best reflector of infrared light, and infrared is the key to Webb's power. Unlike Hubble, which primarily observes visible light, Webb sees the universe in infrared wavelengths. This allows it to peer through cosmic dust that blocks visible light, to see the heat signatures of distant objects, and most importantly for our story, to detect the specific wavelengths of light absorbed by molecules in planetary atmospheres. Water, methane, carbon dioxide. Each molecule absorbs light at specific infrared wavelengths, creating a unique fingerprint that Webb can detect. To see infrared light clearly, Webb had to be cold, extremely cold. The telescope operates at temperatures around minus 223 degrees Celsius, just 50 degrees above absolute zero. To achieve this, it sits behind a tennis court-sized sunshield made of 5 layers of material thinner than a human hair, each layer blocking more of the sun's heat, creating a temperature difference of about 300 degrees Celsius between the hot side facing the sun and the cold side where the instruments operate. Webb orbits not around Earth, but around the Sun at a point called the second Lagrange point, or L2. About 1 million miles from Earth in the direction away from the Sun. At this location, the gravitational pulls of the Earth and Sun balance in just such a way that the telescope can maintain its position relative to Earth with minimal fuel expenditure, while keeping its sunshield constantly between itself and the Sun, Earth and Moon all at once. The telescope has 4 main instruments, but for detecting exoplanet atmospheres, the most important are the near-infrared spectrograph and the mid-infrared instrument. These devices don't take pictures in the traditional sense. Instead, they split light into its component wavelengths, creating a spectrum, a graph showing how much light exists at each specific wavelength. When a planet passes in front of its star, these instruments measure how the star's light changes as it filters through the planet's atmosphere, revealing which wavelengths are absorbed by which molecules. This technique, called transmission spectroscopy, is what allowed Webb to detect water on our 26 light-year distant world. As the planet transited its star, Webb measured the starlight filtering through the planet's atmosphere. Water molecules in that atmosphere absorb specific wavelengths of infrared light, creating telltale dips in the spectrum at exactly the wavelengths we associate with H2O. The signal was clear, repeatable, and unmistakable. What's remarkable is that we're essentially seeing the shadow of an atmosphere, detecting the presence of molecules from the way they interact with light that has travelled for 26 years to reach us. We're reading the chemical composition of air we'll never breathe around a world we've never seen, using reflected light from a star we can barely see with our naked eyes. This is the power Webb brings to our search for worlds beyond our own, and this brings us to the crucial question: why does finding water matter so much? Water is not rare in the universe. This might surprise some people, but the cosmos is actually quite full of water. We found it frozen on Mars, liquid beneath the ice shells of Europa and Enceladus, as vapour in the atmospheres of gas giants, as ice crystals in comets, as massive clouds floating in interstellar space. Water, that simple molecule of 2 hydrogen atoms and 1 oxygen atom, forms readily wherever the conditions allow. Because hydrogen and oxygen are among the most abundant elements in the universe. So why does finding water on this particular world matter so much? The answer lies not in the water itself, but in the context where we found it. First, this is a rocky planet, not a gas giant. Rocky planets like Earth, Mars, Venus, and Mercury form closer to their stars where temperatures during the solar system's formation were high enough that light gases like hydrogen and helium were blown away, leaving behind heavier elements to form solid worlds. Finding water on a rocky planet means we're looking at a world that might have a solid surface, continents and oceans, geology and weather, the kinds of planetary features we can actually envision. Second, this planet appears to be in what astronomers call the habitable zone, sometimes known as the Goldilocks zone, the orbital distance from its star where temperatures might allow liquid water to exist on the surface. Not too hot that all water boils away. Not too cold that it's permanently frozen, but just right. The habitable zone is where life as we know it could potentially exist, because every form of life on Earth requires liquid water. Third, and perhaps most importantly, the presence of water vapour in this planet's atmosphere suggests an active water cycle. Water evaporates from the surface, rises into the atmosphere, condenses into clouds, and rains back down. This cycle is crucial for climate regulation, for weather patterns, for the kind of dynamic planetary chemistry that makes Earth habitable. A water cycle means the planet isn't dead, isn't a frozen ice ball or a scorched desert, but a living, changing world. On Earth, water is everywhere life exists. We find life in the deepest ocean trenches, in underground lakes buried miles beneath Antarctica's ice, in clouds, in volcanic hot springs, in the driest deserts after rare rainfalls. Water is the universal solvent, the medium in which the chemistry of life takes place. Every protein in your body exists in solution with water. Every cell is essentially a tiny bag of carefully controlled water with dissolved chemicals. Our very thoughts happen in neurons floating in cerebral spinal fluid. This doesn't mean life must use water. We can imagine biochemistries based on other solvents, life forms using liquid methane like some of Saturn's moons, or ammonia, or something we haven't even conceived of. But the only life we know, the only life we can study and understand, absolutely requires water in liquid form. So when we search for life beyond Earth, we search for water. It's not the only thing we need to find, but it's a necessary first step. What makes this discovery particularly exciting is that it's not just water in some frozen moon's subsurface ocean or in a gas giant's clouds. This is water in the atmosphere of a rocky planet at the right distance from its star. This is the kind of world where we might find not just water, but living water. Water that supports something beyond chemistry alone. Of course, water is not sufficient for life. You also need the right chemistry, the right elements, carbon and nitrogen and phosphorus, energy sources to drive chemical reactions, time for evolution to work its slow wonders. But water is the foundation. Water is where we start. And now we know, with certainty, that 26 light-years away, that foundation exists. The question becomes, what else is there? What is this world actually like? We've never seen this planet. Not directly. We likely never will, not with current technology. What we have detected is indirect evidence, the slight dimming of its star's light as the planet passes in front, the spectrum of that light revealing the atmosphere's composition. From these clues, we build a picture of a world we can only imagine. The planet is likely rocky, with a mass somewhere between Earth and a super-Earth, possibly 1 to 1.5 times Earth's mass. Its radius is similarly close to Earth's, perhaps 10 to 30% larger. This puts it in the category of planets we think might have solid surfaces, unlike gas giants that are all atmosphere with no place to stand. It orbits a red dwarf star, much smaller and cooler than our Sun. Red dwarfs are the most common type of star in our galaxy, making up about 70% of all stars. They're small, dim, and incredibly long-lived, burning their fuel so slowly that even the oldest red dwarfs in the universe, nearly as old as the universe itself, are still shining, and will continue to shine for trillions of years. Our Sun will die, expand into a red giant and fade to a white dwarf long before this planet's star even begins to run low on fuel. Because red dwarfs are so dim, their habitable zones are very close in. A planet has to orbit much nearer to a red dwarf than Earth does to the Sun to receive enough warmth for liquid water. This planet likely completes an orbit in just a few Earth days, perhaps 10 to 30 days. Racing around its small star at a distance closer than Mercury orbits our Sun. Being so close to its star means this planet is likely tidally locked, the way our Moon is tidally locked to Earth. One face of the planet permanently faces the star, baked in eternal sunlight. The other face points away, locked in perpetual night. Between these extremes, in the twilight band where day meets night, conditions might be more moderate. If there are oceans, they might exist in this twilight zone. Fed by ice melting on the day side, freezing again on the night side, creating weather patterns and winds unlike anything on Earth. The atmosphere we detected contains water vapour, but we don't yet know what else might be there. Is there carbon dioxide, methane, oxygen? Each additional molecule we detect tells us more about the planet's chemistry, its geology, potentially its biology. Future observations with Webb and other telescopes will gradually fill in this picture, adding details to our understanding. We don't know if there's a magnetic field protecting this world from its star's radiation. Red dwarfs are known for violent stellar flares, eruptions of energy and charged particles that could strip away an atmosphere over time if there's no magnetic shield. Earth's magnetic field, generated by the churning motion of molten iron in our core, protects us from the Sun's solar wind. We don't know if this distant world has the same protection. We don't know if there are continents and oceans, or if the water exists only as vapour in the atmosphere, or perhaps as a world-spanning ocean with no land at all. We don't know what colour the sky might be, though with a red dwarf star the light would be dimmer and redder than our bright yellow Sun, meaning the sky might be perpetually sunset-coloured, or perhaps nearly dark even at noon. We don't know if there are moons, we don't know if there are seasons, though with such a close, quick orbit, probably not in the way Earth has seasons. We don't know if there are mountains or valleys, volcanoes or glaciers, storms or calm seas. Everything beyond the basic facts, the size, the mass, the presence of water, remains speculation and imagination, but we know it's there. We know it's real, and we know that somewhere in our night sky, among the thousands of stars visible to the naked eye, one of them, though we'd need a telescope to spot it, is being orbited by a world with water in its air, a world that might have oceans, a world that exists within the realm of theoretical human reach. This thought leads us naturally to the question of how we actually detected that water across such vast distances. The method we use to detect water and other molecules in exoplanet atmospheres is both elegantly simple in concept and extraordinarily difficult in execution. It's called transmission spectroscopy, and it relies on one of the fundamental principles of chemistry and physics. Every molecule absorbs and emits light at specific wavelengths. Imagine you're looking at a bright light bulb through a coloured glass window. The glass absorbs certain colours of light and allows others to pass through. A red window absorbs blue and green light, letting only red through. What reaches your eye is not the complete spectrum of the light bulb, but a filtered version, missing the colours the glass absorbed. Now imagine that instead of coloured glass, you're looking through a gas filled with specific molecules. Each type of molecule absorbs specific wavelengths, creating a unique pattern of absorption lines in the spectrum. This is how we read the composition of planetary atmospheres. When a planet passes in front of its star from our perspective, an event called a transit, some of the star's light passes through the planet's atmosphere before reaching us. The molecules in that atmosphere absorb specific wavelengths of light. By measuring precisely which wavelengths are absorbed, we can identify which molecules are present. Water molecules, H2O, absorb infrared light at very specific wavelengths, around 1.4 micrometers, 1.9 micrometers, and 2.7 micrometers. Among others, these absorption features are as distinctive as a fingerprint. When the James Webb Space Telescope observed this planet transiting its star and found absorption at exactly these wavelengths, it was reading water's signature across 26 light-years of space. The challenge is that these signals are incredibly faint. The planet itself is tiny compared to its star. When it transits, it blocks perhaps 1% of the star's light, maybe less. The atmosphere is even smaller, just a thin shell around the planet. The additional dimming caused by the atmosphere absorbing certain wavelengths might be just a few parts per million change in the star's brightness. We're trying to detect a whisper in a thunderstorm, a single drop of ink in a swimming pool. This is why it took the James Webb Space Telescope to make this discovery. Hubble attempted similar observations of other exoplanets and succeeded with some, but Webb's larger mirror, its superior infrared sensitivity, and its stable viewing platform at L2 give it the precision needed to detect these subtle signals clearly. The process involves observing the star multiple times, once when the planet is in front of the star, measuring the combined light of star plus filtered atmosphere, and once when the planet is not in front, measuring just the star alone. By subtracting one measurement from the other, we isolate the effect of the atmosphere. Do this at many different wavelengths across the infrared spectrum, and you build up a graph showing which wavelengths were absorbed, and by how much. Then comes the interpretation. Astronomers compare the observed spectrum to theoretical models of what different atmospheric compositions would produce. A model atmosphere with water vapour will show absorption peaks at the same wavelengths where we detected absorption. Match enough of these features and you can confidently say, water is there. This technique isn't perfect. Clouds in the atmosphere can scatter light and complicate the signal. Different molecules can have overlapping absorption features. The planet's temperature affects how much of each molecule exists as vapour versus liquid versus solid. But with careful analysis, repeated observations to confirm the findings, and sophisticated computer modelling, we can make definitive detections, and that's what happened here. The absorption lines matched water's signature. Multiple observations confirmed it. The model supported it. 26 years after the light left that distant world, filtered through an atmosphere containing water vapour, it reached our telescope and told us its story. The technology to read that story, to decode those absorption lines, represents centuries of work in spectroscopy, chemistry, astronomy, and engineering all coming together. Which naturally leads us to wonder, what else might be in that atmosphere waiting to be discovered? An atmosphere is more than just air. It's the interface between a planet and space, the layer where sunlight becomes warmth, where water evaporates and rains, where weather happens, where life, if it exists, would breathe. Understanding an exoplanet's atmosphere tells us nearly everything about what kind of world it is. For this water world 26 light-years away, we know water vapour is present, but atmospheric science tells us there must be more. A stable atmosphere requires mass, enough gravity to hold gases against the planet's surface. For a rocky planet like this, that atmosphere likely contains heavier molecules that can't easily escape to space. Carbon dioxide is a strong candidate. On Earth, Venus, and Mars, carbon dioxide is produced by volcanic activity as molten rock releases trapped gases. It's also a product of carbon chemistry, which is fundamental to geology and potentially biology. If this planet has active geology, plate tectonics or volcanic activity, carbon dioxide would accumulate in the atmosphere unless removed by weathering or other processes. Nitrogen might be there as well. Earth's atmosphere is 78% nitrogen, an inert gas that forms the background against which other atmospheric chemistry happens. Nitrogen is common in the universe and would be expected in a rocky planet's atmosphere. It doesn't absorb strongly in the infrared wavelengths Webb observes, making it harder to detect, but absence of detection doesn't mean absence of the gas. Methane would be particularly interesting. On Earth, most methane is biological in origin, produced by microorganisms, cattle, wetlands, all the various forms of life that decompose organic matter in low oxygen environments. Methane can also be produced geologically through reactions between water and minerals in the crust. Detecting methane would raise immediate questions about its source. Is it geological or biological? The answer would depend on how much is there, how it's distributed, whether it varies over time, what other gases accompany it. Oxygen would be even more significant. Molecular oxygen, O2, the gas we breathe, is highly reactive. It doesn't persist in an atmosphere unless constantly replenished. On Earth, all the oxygen in our air is produced by photosynthesis, by plants and algae and cyanobacteria, converting carbon dioxide and water into sugars and oxygen. Abiotic processes can produce small amounts of oxygen when ultraviolet light splits water molecules, but nothing like the 21% we have on Earth. Detecting significant oxygen, especially alongside methane, which oxygen reacts with to form carbon dioxide and water, would be a strong biosignature, evidence of life actively maintaining an out-of-equilibrium atmospheric chemistry. We don't yet know if any of these gases are present. Webb's initial observations confirmed water, which was the first priority, the fundamental requirement. Follow-up observations, which may already be underway or planned, will search for these other molecules, gradually building a complete picture of this world's atmospheric composition. There's also the question of clouds. Earth's clouds are made of water, but clouds can form from other substances at different temperatures. Titan, Saturn's largest moon, has clouds of methane. Venus has clouds of sulfuric acid. What might clouds on this world be made of? Would they be in the twilight zone, where day meets night and temperatures allow condensation? Or spread across the entire day side? Or perhaps there are no clouds at all, just clear skies under a dim red sun. The atmosphere's thickness matters too. Earth's atmosphere has a surface pressure of about 14.7 pounds per square inch, the weight of all the air above pressing down. Too thin, and water can't exist as liquid, boiling away even at low temperatures like on Mars. Too thick, and you get a runaway greenhouse effect like Venus, where surface temperatures melt lead. The ideal is somewhere in between, a Goldilocks pressure that allows for liquid water, weather and stable climate. Temperature varies with altitude in an atmosphere, creating layers. On Earth, we have the troposphere where weather occurs, the stratosphere where ozone absorbs ultraviolet light, the mesosphere where meteors burn up, and the thermosphere extending towards space. Each layer has different chemistry, different dynamics. We can't yet resolve these layers on distant exoplanets, but they exist, creating complexity we're only beginning to understand. Every new observation of this planet will add another piece to the puzzle. Each molecule detected, each feature measured, brings us closer to knowing what it's really like to stand on that world, to look up at that alien sky, to breathe that air, if indeed it's breathable at all. And all of this atmospheric chemistry depends on a more fundamental question. Is this planet even in the right place to have liquid water? Let's explore what we mean by the habitable zone. The habitable zone is not as simple as most people think. The concept seems straightforward. There's a range of distances from a star where a planet's surface temperature could allow liquid water to exist. Too close, like Venus, and water boils away. Too far, like Mars, and it freezes solid. In the middle, like Earth, you get oceans. Simple, right? Except it's not simple at all. Habitability depends on far more than just distance from a star. It depends on the planet's atmosphere, which creates greenhouse warming. Venus is too hot not just because it's close to the sun, but because its thick carbon dioxide atmosphere traps heat in a runaway greenhouse effect. Mars is too cold not just because it's far from the sun, but because it lost most of its atmosphere and with it the greenhouse warming that once allowed liquid water on its surface billions of years ago. Habitability depends on the star's type and behaviour. Red dwarfs like this water-world star are dim and cool, so their habitable zones are very close in, where tidal forces lock planets into synchronous rotation. But red dwarfs also produce intense ultraviolet and X-ray radiation and violent stellar flares, especially when young, which could strip away planetary atmospheres. Whether a planet in a red dwarf's habitable zone is actually habitable depends on whether it can maintain an atmosphere in that harsh environment. Habitability depends on planetary mass and gravity. Too small, like Mars, and the planet can't hold onto a thick atmosphere. Gases escape to space. Too large, like Neptune, and the planet might accumulate so much hydrogen and helium during formation that it becomes a gas giant with no solid surface. The habitable zone for planet formation is complicated by planet migration, where worlds form in one location and drift inward or outward over time, potentially entering or leaving the habitable zone after formation. Habitability depends on geological activity. Earth's plate tectonics recycle carbon dioxide, regulating our climate over geological time. Volcanic activity releases gases that replenish the atmosphere. A magnetic field generated by a liquid iron core protects the atmosphere from stellar wind. Without these processes, habitability might be temporary, lasting only millions of years instead of billions. Habitability depends on the presence of a moon. Our moon stabilizes Earth's axial tilt, preventing wild climate swings. It creates tides, which may have been important for the origin of life by creating tidal pools where chemicals could concentrate and react. We don't know if this water world has a moon, but it could matter. Habitability even depends on the planet's neighbours. Jupiter's gravity has both helped and hindered Earth. It deflects some comets that might otherwise strike us, but it also perturbed the orbits of asteroids, sending some our way. The right configuration of planets in a system can maintain long-term stability. The wrong configuration can lead to chaotic orbital changes that eventually throw planets out of the habitable zone. For our water world 26 light-years away, we can say it's in the habitable zone of its star, meaning calculations based on the star's luminosity and the planet's distance suggest temperatures could allow liquid water. The detection of water vapour in the atmosphere supports this, suggesting the planet is neither so hot that all water is baked off, nor so cold that it's entirely frozen. But truly habitable? That's a much harder question. Is the atmosphere thick enough but not too thick? Is there geological activity maintaining it? Is there a magnetic field protecting it? Has it been stable for billions of years, long enough for life to evolve? Or did it only recently migrate into the habitable zone and hasn't yet developed the complex chemistry life requires? These questions can't be answered from spectra alone. They require decades of observations, studying how the planet changes over time, building models of its interior structure and dynamics, possibly even detecting biosignatures that would prove life has found a way despite the challenges. What we can say is this: the planet is in the right neighbourhood. The fundamental requirements, liquid water, appropriate temperature, likely rocky composition, are met. Whether that translates to actual habitability, to life, to a world we could one day visit, remains to be seen. But the foundation is there, and that makes this world endlessly fascinating to study. And all of this depends on the star itself, the sun this water world orbits. Let's turn our attention there. The star at the centre of this system is fundamentally different from our own sun, and understanding those differences helps us understand what this water world might experience on a daily basis. Our sun is a G-type main sequence star, what astronomers call a yellow dwarf, though it's actually white when seen from space. It has a surface temperature of about 5,500 degrees Celsius, a diameter about 109 times that of Earth, and a mass 330,000 times Earth's mass. It's been shining steadily for 4.6 billion years and will continue for another 5 billion years before beginning its transformation into a red giant. This water world orbits an M-type main sequence star, a red dwarf, far smaller and cooler than our Sun. Red dwarfs have surface temperatures between 2,500 and 4,000 degrees Celsius, diameters roughly 10 to 60% of the Sun's, and masses between 8 and 60% of the Sun's mass. They're the universe's misers, burning their hydrogen fuel so slowly and efficiently that even the smallest red dwarfs will shine for 6 to 12 trillion years, far longer than the current age of the universe. Because they're so small and cool, red dwarfs emit most of their light in infrared wavelengths. If you could see one up close, it would glow deep red, or perhaps orange, quite different from our yellow sun. A planet in the habitable zone would receive dimmer, redder light. Photosynthesis, if it evolved there, would need to work with different wavelengths. Plants, if they existed, might be black to absorb as much light as possible, rather than green-like on Earth. The habitable zone around a red dwarf is much closer to the star than Earth is to the Sun. While Earth orbits at 93 million miles, receiving just the right amount of warmth, this water world likely orbits at just a few million miles, close enough to complete an orbit in days rather than a year. At that distance, the star would appear enormous in the sky, perhaps 20 or 30 times larger than our Sun appears from Earth, a huge dim red disk dominating the horizon. Being so close has consequences. Tidal forces increase with proximity, and at these distances they're strong enough to tidally lock the planet, forcing it to always show the same face to its star. This creates the permanent day side and permanent night side we discussed earlier, with all the climate implications that come with such a configuration. Red dwarfs are also famously active, especially young ones. They produce stellar flares, sudden eruptions of magnetic energy that release enormous amounts of radiation, particularly in ultraviolet and X-ray wavelengths. These flares can be thousands of times more powerful than solar flares from our Sun, and they happen frequently, sometimes multiple times per day. For a planet orbiting close enough to be in the habitable zone, these flares could be devastating, stripping away atmosphere, sterilizing the surface, making life's emergence difficult or impossible. However, this particular star is likely mature, having settled down from its violent youth. Older red dwarfs flare less frequently and less intensely, and if the planet has a strong magnetic field, it could deflect much of the stellar wind and radiation, creating a protective bubble like Earth's magnetosphere does for us. The star's longevity is, in some ways, a beautiful thing to contemplate. Our Sun will eventually die. In 5 billion years, it will swell into a red giant, consuming Mercury, Venus, and possibly Earth, before shedding its outer layers and fading to a white dwarf, a slowly cooling ember in space. But this red dwarf will keep shining. It will outlive our Sun by trillions of years. The water world orbiting it has, in principle, trillions of years ahead of it, time enough for life to evolve, flourish, evolve again, develop intelligence, build civilizations, and potentially even look up at their night sky and wonder if anyone else is out there, perhaps even detecting our sun's light and wondering if life exists here. There's something profound about the fact that red dwarfs, the smallest and dimmest stars, the ones we can't even see with our naked eyes from light years away, are also the longest lived, the most stable in the long run, the ones that will still be shining when all the bright stars we admire in our night sky have long since burned out and gone dark. This water world orbits one of these patient stars, receiving its dim red light, warmed by a sun that will outlive almost everything else in the galaxy. And the water on that world, the water vapour in its atmosphere that Webb detected, has a story of its own about how it came to be there. Let's trace that journey. Water is older than Earth, older than our Sun. The hydrogen atoms in water, H2O, were created in the Big Bang 13.8 billion years ago. The oxygen atoms were forged in the cores of massive stars billions of years ago, then scattered into space when those stars exploded as supernovae. The water molecule itself, the combination of hydrogen and oxygen, has been forming and reforming throughout cosmic history. When a new star system begins to form from a cloud of gas and dust, water is already there, frozen as ice on dust grains floating in the cloud. As the cloud collapses under its own gravity, spinning faster, flattening into a disk around the forming star, those ice-coated dust grains collide and stick together, growing from microscopic specks into pebbles, into boulders, into planetesimals, the building blocks of planets. Close to the young star, temperatures are too high for ice to survive. Water sublimates, turning directly from ice to vapour, and then either blows away in the stellar wind or gets incorporated into the star itself. This is why the inner rocky planets in our solar system, Mercury, Venus, Earth and Mars, formed relatively dry. Most of the water we have on Earth arrived later, delivered by asteroids and comets from the outer solar system where ice could survive. But around a red dwarf, the habitable zone is much closer to the star, yet because the star is so dim and cool, temperatures there might be low enough for water ice to exist during planet formation. This water world might have incorporated water directly during its formation, starting with a water-rich composition from the very beginning. Alternatively, like Earth, it might have formed dry and received water later through bombardment by comets and water-rich asteroids. Early in a solar system's history, planetary formation is chaotic. Planetesimals collide, merge, break apart. Gravity stirs the orbits, sending some objects inward toward the star, others outward. A forming planet in the habitable zone would be struck repeatedly by incoming debris, some of which would carry water. Over millions of years, this bombardment would deliver vast quantities of water. Each impact brings ice that melts on impact or vaporizes, and then rains down. Gradually. The planet accumulates an ocean's worth of water, maybe more. On Earth, we have about 1.4 billion cubic kilometers of water, roughly 332 million cubic miles. It sounds like a lot, and it is in absolute terms, but it's less than 1% of Earth's total mass. Most of our planet is rock and metal. The water is just a thin film on the surface. Once water accumulates on a planet, it begins to shape that world. Liquid water weathers rock, breaking it down chemically and physically. It carries minerals in solution, concentrating them in some places, depleting them in others. It creates an environment where certain chemical reactions can occur that wouldn't happen in dry conditions. It enables erosion, carving valleys, wearing down mountains, creating soil. If the planet has an atmosphere, water evaporates from the surface, rises into the air, condenses into clouds, and rains back down. This cycle distributes heat around the planet, moderating temperatures. It creates weather, winds, storms. On Earth, the water cycle is intimately connected to climate, regulating global temperature through feedback mechanisms involving clouds, ice, and ocean currents. Water also plays a crucial role in plate tectonics, at least on Earth. Water in the mantle makes rock more malleable, allowing the slow convection that drives plate movements. Water at subduction zones, where one tectonic plate slides beneath another, lowers the melting point of rock, creating the magma that feeds volcanoes. Without water in Earth's interior, plate tectonics might not work the way they do. And of course, water is the medium of life. Every biochemical reaction that makes you alive happens in water. The first cells likely emerged in water, possibly in hydrothermal vents on the ocean floor, where mineral-rich hot water meets cold ocean, creating chemical gradients that early life could exploit for energy. Water's unique properties, its ability to dissolve so many substances, its liquid range at common planetary temperatures, its expansion when frozen making ice float, all these properties make it ideal for life. So when we detect water on this distant world, we're not just finding a molecule. We're finding a substance with a deep cosmic history, a substance that shapes planets and potentially enables life, a substance that connects that world to Earth, and to the broader story of how chemical elements become planets, and life and everything we know. The water that Webb detected in that planet's atmosphere has been on a journey that spans billions of years and countless light years of space. And it waits there now, vapour in an alien sky, perhaps raining down onto an ocean we've never seen, on a world we can only dream of visiting. This dream of detection and discovery didn't begin with James Webb. It's part of a much longer human story. Let's step back and see where this search came from. The search for planets around other stars is an old dream, but a young science. For thousands of years, humans looked up and wondered if those points of light in the night sky might have worlds of their own. But wondering and knowing are very different things, and until remarkably recently we had no way to know. The first confirmed detection of an exoplanet around a sun-like star came in 1995, when Swiss astronomers Michel Mayer and Didier Queloz announced they'd found a planet orbiting the star 51 Pegasi. The discovery was revolutionary, earning them the Nobel Prize in Physics in 2019. The planet, dubbed 51 Pegasi b, was nothing like anyone expected. A gas giant larger than Jupiter, orbiting closer to its star than Mercury orbits our Sun, completing an orbit every 4 days. It shouldn't have existed there according to planet formation theories of the time, but it did. That discovery opened the floodgates. Within years, dozens of exoplanets were confirmed. Within 2 decades, thousands. Today, we've confirmed over 5,000 exoplanets and have thousands more candidates awaiting verification. We've found gas giants and rocky worlds, planets larger than Jupiter and smaller than Mercury, planets orbiting close to their stars and far away, planets in multi-star systems, rogue planets floating free in space without any star at all. The methods we use to find these worlds have evolved. The earliest discoveries used radial velocity measurements, detecting the tiny wobble a planet's gravity causes in its star's motion. Imagine a figure skater spinning with arms outstretched holding weights. The weights pull on the skater, making them wobble slightly. Similarly, a planet pulls on its star, causing it to wobble back and forth. By measuring the star's light very precisely, we can detect this wobble as a Doppler shift, the star moving slightly toward us, then slightly away, over and over with each orbit. Then came the transit method, watching for the tiny dimming when a planet passes in front of its star. This is extraordinarily difficult. A Jupiter-sized planet transiting a Sun-like star dims it by about 1%. An Earth-sized planet causes a dimming of less than 1/100%. You need extremely precise instruments, stable viewing conditions, and a lot of patience, since transits only happen when the planet's orbit is aligned edge-on to our view. The Kepler Space Telescope, launched in 2009, revolutionized exoplanet science through the transit method. Kepler stared at a single patch of sky containing about 150,000 stars, measuring their brightness constantly for 4 years. It found thousands of planets, dramatically increasing our senses of worlds beyond our solar system. Kepler showed us that planets are common, that nearly every star has planets, that Earth-sized worlds in habitable zones exist around many stars, but Kepler could only detect planets. It couldn't study their atmospheres. That required a different approach, transmission spectroscopy, the method we discussed earlier. The Hubble Space Telescope pioneered this technique, making the first detections of atmospheric composition on exoplanets in the early 2000s. Hubble found sodium in the atmosphere of a hot Jupiter, found water vapour on several worlds, proved that we could actually analyse these distant atmospheres. The Spitzer Space Telescope. Another infrared space observatory contributed as well, studying exoplanet atmospheres and even creating crude temperature maps of hot Jupiters, showing how temperature varies between their day and night sides. Each of these missions built on the last improving techniques, refining instruments, learning what works and what doesn't, and each mission made clear what the next one would need. Hubble showed us we could study exoplanet atmospheres but needed a bigger mirror and better infrared capabilities. Kepler showed us where to look but couldn't tell us what those worlds were like. Spitzer pushed infrared observations but was limited by its small mirror and warm operating temperature. All of this led to James Webb, a 6.5 metre mirror operating at 50 degrees above absolute zero, observing in infrared wavelengths, specifically designed to study exoplanet atmospheres among its other science goals. Webb is the culmination of decades of learning, the next step in a journey that began with simply trying to find exoplanets, and now allows us to analyse their chemical composition from light years away. The water detection on this 26 light-year distant world is part of this continuum. It's not the first exoplanet water detection, but it is one of the most significant because of the planet's size, location and potential habitability, and it certainly won't be the last. Webb is just beginning its mission, with potentially 20 years of operation ahead. Every year it will observe more exoplanets, detect more molecules, build our understanding of what these worlds are truly like. And this world isn't alone. Let's put it in context with the other water worlds we've discovered. The universe, it turns out, is full of water. This shouldn't surprise us given how common the constituent elements are, but seeing it confirmed observationally, world after world, is still remarkable. We've detected water vapour in the atmospheres of numerous hot Jupiters, gas giant planets orbiting very close to their stars. These aren't habitable, they're scorching hot, with atmospheric temperatures reaching thousands of degrees, hot enough to vaporise rock. But water is there, along with other molecules like carbon monoxide, methane, and sometimes even exotic compounds like titanium oxide that form only at extreme temperatures. We've found water on super-Earths and mini-Neptunes, planets larger than Earth but smaller than Neptune, whose exact composition we're still trying to understand. Some might be scaled-up rocky planets with thick atmospheres. Others might be water worlds, planets where water makes up a significant fraction of their mass, creating global oceans hundreds of kilometres deep over a high-pressure ice mantle. One particularly famous example is K2-18b, a planet about 8.6 times Earth's mass orbiting a red dwarf 120 light-years away. In 2019, astronomers announced detecting water vapour in its atmosphere using Hubble data. Follow-up observations with Webb in 2023 found not just water, but also carbon dioxide and possibly dimethyl sulfide, a molecule that on Earth is only produced by life, specifically by ocean phytoplankton. The dimethyl sulfide detection is still debated, and even if confirmed, there are possible abiotic explanations. But K2-18b represents a fascinating target for continued study, a potentially habitable world where we might, just might, have detected the first tentative hints of biological processes. Then there's the TRAPPIST-1 system, 40 light-years away, containing 7 Earth-sized planets, orbiting an ultra-cool red dwarf. At least 3 of those planets are in the habitable zone. Webb has observed several of them, searching for atmospheres. Some appear to be rocky and airless, scoured clean by stellar radiation, but others might have atmospheres, and ongoing observations are trying to determine their composition. If water is found there, it would make the TRAPPIST-1 system an incredible laboratory for studying planetary evolution around red dwarfs. Closer to home, we found abundant water in our own solar system. Mars once had rivers, lakes, possibly oceans on its surface, all of which dried up as its atmosphere thinned. Europa, a moon of Jupiter, has a global ocean of liquid water beneath an icy crust, containing perhaps twice as much water as all of Earth's oceans combined. Enceladus, a small moon of Saturn, has a subsurface ocean that vents into space through geysers at its south pole. We've literally tasted that water with spacecraft flying through the plumes, analysing its composition. Even bodies we thought were dry turn out to have water. The moon, which we long believed was bone dry, has water ice in permanently shadowed craters at its poles. Mercury, the closest planet to the Sun, also has water ice in its polar craters, where sunlight never reaches and temperatures stay cold enough for ice to persist despite the scorching heat just a few degrees of latitude away. Comets are essentially dirty snowballs, water ice mixed with rock and organic compounds. Asteroids in the outer asteroid belt contain significant water ice. The Kuiper belt and Oort cloud, the distant reservoirs of comets beyond Neptune, contain more water ice than exists in all the liquid water in all the oceans on all the planets combined. Water is everywhere. And yet, liquid water, water in the right temperature range on a world with the right conditions, remains rare and precious. Most of the water in the universe is frozen solid or boiled to vapour. The narrow temperature range where water is liquid, from 0 to 100 degrees Celsius at Earth's atmospheric pressure, is unusual in cosmic terms. Most places are too cold or too hot. This makes the discovery on our 26 light-year distant world particularly meaningful. Yes, we've found water before, on hot Jupiters and frozen moons and in the clouds of comets. But finding it in the atmosphere of a potentially habitable rocky planet, finding it in a location and form where it could support life, that's still special. That still narrows the field of where we should look for biology beyond Earth. Each water world we discover teaches us something. The hot Jupiters show us that water survives in extreme conditions. The icy moons show us that liquid water can exist far from the sun's warmth, if other energy sources like tidal heating are present. The potentially habitable worlds like K2-18b and now this 26 light-year distant planet show us that the conditions we think necessary for life, liquid water on a rocky world in a habitable zone, actually exist out there. Not just theoretically, but actually, observably, confirmably. But water alone doesn't make a world habitable, doesn't guarantee life. There are other requirements, other pieces of the puzzle. Let's consider what else is needed. Life as we know it requires more than just water. It requires a specific set of chemical elements, energy sources, time, and probably a bit of luck. Understanding these requirements helps us assess whether a water world like this one might actually be inhabited. First, the elements. Life on Earth is built from carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, often abbreviated CHNOPS. Carbon is particularly crucial. It forms the backbone of all biological molecules, proteins, DNA, fats, carbohydrates. Carbon's ability to form stable bonds with up to 4 other atoms, including other carbon atoms, allows for the enormous chemical complexity life requires. Fortunately, all of these elements are abundant in the universe. Carbon is forged in stars, scattered into space when stars die. Nitrogen and oxygen are similarly products of stellar nucleosynthesis. Hydrogen is left over from the Big Bang. Phosphorus and sulfur are created in supernovae. Any rocky planet should have access to these elements in various mineral forms. But having the elements isn't enough. They need to be in the right form, available for chemistry. Locked up in rocks, carbon is useless for life, but dissolved as carbon dioxide in water, or present as organic compounds, it becomes accessible. Life needs elements in chemical forms that can react, combine, break apart, rearrange into the molecules biology requires. Second, energy. Life is not in equilibrium. It actively maintains itself against entropy, building complex structures from simpler components, requiring energy input to do so. On Earth, most life ultimately depends on sunlight captured by photosynthesis. Plants, algae, and cyanobacteria convert light energy into chemical energy stored in sugars, which then feeds the entire food chain. But not all life depends on sunlight. Around deep-sea hydrothermal vents, where sunlight never reaches, ecosystems thrive on chemical energy. Using the reaction between hot mineral-rich vent water and cold ocean water to power their metabolism. A potentially habitable water world could use either energy source or both. If it has liquid water on the surface, it likely receives enough starlight for photosynthesis. If it has geological activity, it might have hydrothermal vents providing chemical energy. The key is that energy must be available in a form life can use, must be steady and sustained over long periods, and must not be so intense as to sterilize the surface. Third, time. Life on Earth didn't appear instantly. The oldest evidence of life dates to about 3.8 billion years ago, just a few 100 million years after Earth's surface cooled enough for liquid water to exist. But those first life forms were simple, single-celled, nothing like the complex organisms we see today. It took billions of years for complex cells with nuclei to evolve, nearly 4 billion years for multicellular life. About 4.5 billion years for intelligent life to emerge. If life on another world follows a similar timeline, that world needs billions of years of stable conditions. The habitable zone needs to remain habitable. The atmosphere needs to persist. Stellar activity needs to calm down enough not to repeatedly sterilize the surface. This is one concern with red dwarf planets. Red dwarfs live for trillions of years, giving plenty of time for life to evolve. But they also flare violently when young. Whether life can emerge and persist through that violent phase is an open question. Fourth, solvents and chemistry. We've focused on water as a solvent, but chemistry also requires the right conditions. Temperature affects reaction rates. Too cold and reactions happen too slowly for life to maintain itself. Too hot and complex molecules break apart faster than they can be built. Pressure matters too. pH, the acidity or alkalinity of water, affects what reactions can occur. On Earth, life exists across an enormous range of temperatures, from minus 15 degrees Celsius in Arctic sea ice to 121 degrees Celsius in deep sea vents, and across a wide pH range from highly acidic to highly alkaline environments. But each type of life is adapted to its specific conditions. Fifth, and this is speculative, perhaps some amount of chance. Did life on Earth emerge because the conditions were perfect, making life's origin inevitable? Or was there a random element, a lucky combination of circumstances that happened to occur here, but might not occur elsewhere, even with similar conditions? We don't know. We have only one example of life's origin to study, our own, and from a single example you can't calculate probabilities. This uncertainty is why finding life elsewhere would be so profound. If life emerged independently on another world, it would suggest that life is common, that given the right conditions, chemistry naturally organizes itself into biology. If we explore many worlds with the right conditions and find life nowhere, that would suggest we're rare, that Earth's biosphere is unusual, that the conditions we think are sufficient might actually not be. For our water world 26 light years away, we can check off some boxes. Water, yes. Rocky planet, likely. Habitable zone, yes. CH-NOPS elements, almost certainly present in some form. Energy from starlight, yes. Time, the star is probably billions of years old, giving time for any potential life to evolve. What we don't know is whether all these ingredients combined in the right way. whether life emerged, whether it survived, whether it evolved into anything complex. These are the questions we're trying to answer by studying worlds like this one observation at a time. And there's something else to consider, something that makes this discovery even more poignant. The light we're seeing, the information we've gathered, is 26 years old. We're looking into the past. When you look at the night sky, you're looking into the past. Light from the moon takes 1.3 seconds to reach Earth, so you see the moon as it was 1.3 seconds ago. Light from the sun takes 8.3 minutes, so you see the sun as it was 8.3 minutes in the past. If the sun suddenly vanished, we wouldn't know for 8.3 minutes. The nearest star, Proxima Centauri, is 4.2 light years away. When you look at it, you see it as it was 4.2 years ago. If Proxima Centauri exploded today, we wouldn't see the explosion until 2029. This water world is 26 light years away. Every photon of light from that system that reaches us has been travelling for 26 years. The light Webb detected, the starlight that passed through the planet's atmosphere and carried the signature of water vapour, left that star in 1997. Think about what was happening in 1997. The first Harry Potter book was published. The Mars Pathfinder rover landed on Mars. Scientists first cloned a sheep dolly. The world was different. Many of the people watching this video were children, or not yet born. Technology was different. We had no smartphones, no social media as we know it today, no YouTube, no streaming services, dial-up internet was still common. The International Space Station was still being assembled. And on a planet 26 light-years away, at that moment in 1997, water vapour existed in the atmosphere. A planet was orbiting its star, as it had been for millions or billions of years. Weather was happening, if there's weather there. Chemistry was occurring. And sunlight, dim red light from a small cool star, was reflecting off the planet's atmosphere. Some of that light angling toward Earth, beginning a journey that would last 26 years. That light travelled through space, empty and dark and cold, at 186,000 miles per second, never slowing, never stopping. It passed other stars, though none close enough to interact with the light. It traversed the space between stars, the interstellar medium, which is not quite empty but contains about 1 atom per cubic centimetre, enough to very slightly scatter and absorb the light over such distances. Year by year, the light travelled. 1998. 1999, 2000, 2001. Through all the events of those years, through changes on Earth, through technological progress and political upheaval, through the lives and deaths of millions of people, the light kept coming, indifferent to human affairs, carrying information about a distant atmosphere. 2021, Webb launched. 2022, Webb deployed, calibrated, began observations. 2023. The light that left in 1997 finally arrived, was collected by Webb's mirror, focused onto its instruments, split into a spectrum, analysed, and we discovered water. But here's the truly mind-bending part. We're seeing the planet as it was in 1997. We don't know what that planet is like now, today, in 2025. We won't know for another year, when light that left in 2024 finally reaches us. Everything we observe is history. The planet could have changed. A massive volcanic eruption could have altered its atmosphere. A comet could have struck it. Life could have emerged in the intervening 26 years, or gone extinct, or evolved from microbes into something more complex. We're fundamentally disconnected from the present state of everything beyond our solar system. Even our nearest neighbouring stars, we see them as they were years ago. For this water world, the lag is substantial, an entire generation of human life. A child born in 1997 is now 27 years old, possibly watching this video. They're the same age as the light we're studying. This temporal lag becomes even more significant when we think about communicating with any potential life on that world. Suppose, impossibly, we detected a signal indicating intelligent life there. A radio transmission, clearly artificial, saying hello or whatever the equivalent might be, that signal would be at least 26 years old when we received it. If we sent a reply, it would take 26 years to reach them. Their response would take another 26 years to come back. A single exchange of messages would take 52 years, longer than many human careers. Any conversation with another civilization at such distances would be multi-generational. The people who sent the first message would be retired or deceased by the time a reply arrived. Space exploration at these distances requires thinking in timescales beyond individual human lives, requiring continuity of purpose across decades, across generations. And yet, 26 light-years is close, genuinely close in cosmic terms. There are stars we can see with our naked eyes that are thousands of light-years away. The centre of our galaxy is 26,000 light-years distant. The Andromeda Galaxy, our nearest large galactic neighbour, is 2.5 million light-years away. Light from Andromeda that you see tonight left when our ancestors were Australopithecus, upright walking apes not yet fully human. In that context, 26 years is nothing. It's contemporary, practically real time. It's close enough that the universe hasn't changed much in the interval. Stars have the same positions. The cosmic microwave background has cooled by an immeasurably tiny amount. By cosmic standards, we're seeing this water world as it is now, even though now is a philosophically complicated concept when relativity is involved. This temporal dimension adds a layer of poignancy to the discovery. Somewhere out there, 26 light-years away, a planet exists right now. It may have water on its surface, clouds in its sky, weather, seasons, chemistry, possibly life, but we won't know about any of that for 26 years. We're always looking backward, always analysing the past, always separated from the present by the speed of a light. And if we sent a mission there, the lag would be even more pronounced. But before we dream of going, we should ask, why haven't we heard anything? Why the silence? The Fermi paradox is named after physicist Enrico Fermi, who famously asked during a lunch conversation in 1950, quote 2, "The paradox is this. The universe is vast and old, containing hundreds of billions of galaxies each with hundreds of billions of stars, many of which have planets, some of which must be habitable. If intelligent life is common, the galaxy should be teeming with civilizations. Some should be older than us, more advanced, capable of interstellar travel or at least interstellar communication. So why haven't we seen any evidence of them? Why is the sky silent? For our water world 26 light-years away, the silence is particularly pointed. If there's intelligent life there, advanced enough to build radio transmitters, we should be able to detect their signals. We've been listening to space with radio telescopes since the 1960s, conducting SETI, the search for extraterrestrial intelligence. We've listened to hundreds of stars, including many nearby ones, searching for patterns in the radio noise that might indicate artificial origin. We've found nothing, no clearly artificial signals. No repeating mathematical sequences, no encoded messages, no evidence of anyone trying to communicate. The galaxy, at least at the radio frequencies we've monitored, seems quiet. There are many possible explanations, none of them definitive, all of them speculative. Let's consider a few. First, perhaps life is common, but intelligent life is rare. Earth's history shows that life emerged quickly, within a few 100 million years of conditions becoming suitable, but it remained simple for billions of years. Intelligence, technological civilization, only appeared in the last few 100,000 years, and radio technology only in the last century. Perhaps the filter, the barrier that few life forms cross, is the step from simple to complex life, or from complex life to intelligence, or from intelligence to technology. Second, perhaps civilizations don't last long. Humanity has had radio for about 125 years. We've had nuclear weapons for 80 years. We're currently facing climate change, environmental degradation, political instability. Perhaps civilizations typically destroy themselves shortly after reaching technological capability, either through war, environmental collapse, or some other catastrophe. If civilizations last only a few centuries after reaching our level, the galaxy might have many civilizations but spread out in time, never overlapping in their communicative phases. Third, perhaps they're not broadcasting. Communication requires energy, resources, and a reason to reach out. Maybe most civilizations focus inward, on virtual realities or other pursuits, rather than shouting into the void of space. Or maybe they've moved beyond radio, using communication methods we haven't discovered yet or can't detect. Or maybe they listen but don't transmit, for fear of attracting attention from potentially hostile others. Fourth, perhaps space is too big. Even 26 light-years is a vast distance. A radio signal from this water world, if anyone there was broadcasting in the 1990s, would be incredibly faint by the time it reached us, spread out over a sphere with a radius of 26 light-years, diluted almost beyond detection. Unless they were specifically beaming a powerful signal directly at us, we might not be able to detect it above the background noise of the universe. Fifth, perhaps we're early. The universe is 13.8 billion years old, but the first stars formed only about 100 million years after the Big Bang, and those first stars were massive, short-lived, exploding quickly as supernovae. The elements necessary for rocky planets and life, carbon, oxygen, nitrogen, weren't abundant until several generations of stars had lived and died, enriching the galaxy with heavy elements. Maybe Earth-like planets only became common in the last few billion years. Maybe we're among the first civilizations to arise. Or sixth, and perhaps most unsettling, perhaps we're alone. Perhaps the origin of life is so improbable, or the step from simple to complex so unlikely, or the emergence of intelligence so rare that we're the only technological civilization in our galaxy, possibly in our observable universe. Perhaps in all those hundreds of billions of stars, Earth is unique. We don't know which explanation is correct, if any of them are. We have one data point: ourselves. We know life can happen at least once. Beyond that, everything is speculation. For this water world 26 light-years away, if there's any civilization there, they face the same questions we do. If they've detected our sun, if they've observed Earth transiting it and analysed our atmosphere, they've found oxygen and methane, clear biosignatures, and possibly even pollutants indicating industry. They could know we're here, know there's life on Earth, possibly even suspect we're intelligent. But they haven't sent us a signal, or if they have, it hasn't reached us yet or we haven't recognised it. The silence goes both ways. We haven't heard them, and as far as we know, they haven't heard us. This silence makes each new discovery, each potentially habitable world, both exciting and a little melancholic. We find these worlds, we study them, we wonder if anyone is there, and we receive no answer. Just more data, more spectra, more molecules detected, but no voice, no message, no confirmation that we're not alone. Still, the search continues. We keep listening, keep observing, keep discovering new worlds. Because not knowing is perhaps harder than finding nothing. The possibility that someone might be out there, on a world like this one, looking back at us and wondering the same things, is too profound to ignore. And it raises perhaps the most exciting possibility of all. Not just communicating with them, but going there ourselves. Let's turn to that beautiful, impossible dream. Let's be honest about where we stand technologically. Travelling 26 light-years is, with current technology, completely impossible within any reasonable time frame. But understanding our current capabilities gives us a baseline from which to imagine how we might improve. The fastest human-made object ever is the Parker Solar Probe, launched in 2018 to study the Sun. In its close approaches to the Sun, using gravity assist to accelerate, Parker has reached speeds of about 430,000 miles per hour, or roughly 0.064% the speed of light. At that speed, it would take about 41,000 years to travel 26 light-years. The Voyager 1 probe, launched in 1977 and now in interstellar space, travels at about 38,000 miles per hour relative to the Sun, about 0.0056% the speed of light. At Voyager's speed, 26 light-years would take 465,000 years. If Voyager were aimed at this water world, it wouldn't arrive until the year 467,425, by which time human civilization, if it still exists, would be unrecognizable. New Horizons, which flew by Pluto in 2015, is travelling at about 36,000 miles per hour after its Pluto flyby, roughly the same speed class as Voyager. Pioneer 10 and 11, launched in the 1970s, are slower, moving at about 27,000 miles per hour. Our current propulsion technology is fundamentally limited. We use chemical rockets, burning fuel to produce thrust. The specific impulse, a measure of rocket efficiency, is limited by the chemistry of combustion. The fastest we can accelerate a spacecraft with chemical rockets, even with gravity assist from planets, gets us to maybe 0.1% the speed of light at best, and that's with extremely optimistic assumptions. Nuclear propulsion could theoretically do better. A nuclear thermal rocket, heating hydrogen with a nuclear reactor instead of chemical combustion, could have perhaps twice the specific impulse of chemical rockets. Nuclear electric propulsion, using nuclear power to run ion engines, could achieve higher velocities over time but with very low thrust, requiring years to accelerate. Even with nuclear propulsion, we might reach 1 to 2% the speed of light, reducing the travel time to 1,300 to 2,600 years. These are still multi-generational journeys, voyages that would span dozens or hundreds of human lifetimes. You'd need a generation ship, a self-sustaining spacecraft carrying a population that lives, works, reproduces, and dies aboard the ship, generation after generation, with only the distant descendants of the original crew finally reaching the destination. Such a ship would be enormous, requiring life support for perhaps thousands of people to maintain genetic diversity, agricultural systems to produce food, water recycling, power generation, radiation shielding, artificial gravity or exercise regimens to prevent bone and muscle loss in microgravity. The engineering challenges are immense. You'd need social structures that remain stable over centuries, cultural continuity, education systems passing down knowledge and purpose, governance that doesn't devolve into tyranny or collapse. You'd need redundancy in all critical systems, the ability to repair or replace any component using resources aboard the ship. You'd need to protect against cosmic rays, micrometeorites, equipment failures, possibly even social breakdown, mutiny, or loss of purpose as generations pass and the destination remains distant. And all of this assumes we're willing to commit the resources to build such a ship, to send people on a one-way journey knowing they'll never return, knowing they'll die en route, knowing their children and grandchildren and great-grandchildren will live and die in space. And only their distant descendants might see the goal. We've never built anything remotely like this. The International Space Station, our most complex space structure, houses 6 people and requires regular resupply from Earth. It's not self-sustaining. A generation ship would need to be. There have been studies, theoretical designs, concepts like the Orion project in the 1950s, which proposed propulsion by detonating nuclear bombs behind a massive pusher plate, using nuclear explosions as engines. Orion could theoretically reach several percent the speed of light, but it was never built, partly due to nuclear test ban treaties, partly due to cost, partly because the idea of using thousands of nuclear bombs as propulsion seemed insane even by Cold War standards. More recently, concepts like the Daedalus and Icarus studies proposed fusion-powered spacecraft that could reach 10 to 15% the speed of light. These remain purely theoretical. We haven't even achieved sustained fusion power on Earth, let alone in a spacecraft engine. So with current technology, Interstellar travel to a system 26 light-years away is a journey measured in tens of thousands to hundreds of thousands of years, or at best, with nuclear propulsion we haven't built yet, 1 to 2,000 years. It's not impossible in principle, but it's utterly impractical. Which brings us to the question, what would it take to do better? What technologies might allow us to reach this water world in a single human lifetime, or even less? Let's explore some possibilities, starting with one of the most promising, sailing on light. In 2016, a group of scientists and entrepreneurs announced the Breakthrough Starshot initiative, proposing a method to reach the nearest star system, Alpha Centauri, within 20 years of launch. The concept is elegant and, while technologically challenging, possibly achievable with near-term technology. Use lasers to push tiny spacecraft to a significant fraction of the speed of light. The idea works like this. Instead of carrying fuel, which makes spacecraft heavy and limits their speed, use a large, extremely thin reflective sail, similar to a solar sail but designed for laser light. On Earth, or in orbit, build an enormous array of powerful lasers. Focus those lasers on the sail, and the momentum of the light photons hitting the sail pushes it forward, accelerating it to tremendous speeds. Light has momentum, not much, but some. A 1-watt laser shining on a perfectly reflective surface exerts a force of about 6.7 billionths of a newton. That's tiny. But with a sufficiently powerful laser and a sufficiently light spacecraft, you can achieve meaningful acceleration. Breakthrough Starshot proposes a 100 gigawatt laser array, essentially 100,000 1-megawatt lasers working together, focused on a light sail about 4 meters across, weighing only a few grams, attached to a tiny payload, perhaps a gram-scale microchip containing cameras, sensors, communication equipment, all miniaturized to an extreme degree. With such a setup, the calculations suggest you could accelerate the light sail to 15 to 20% the speed of light within minutes, as it passes through the laser beam's focus. At 20% light speed, you could reach Alpha Centauri 4.2 light-years away in about 20 years. You could reach our water world 26 light-years away in about 130 years. 130 years is still longer than a human lifetime. But it's within the timescale of human civilization. The mission could be launched by one generation, and the data received by their great-grandchildren. Institutions, universities, governments could maintain continuity over such a time frame. But the challenges are significant. Building a 100 gigawatt laser array is an enormous undertaking. For comparison, the entire world's electrical generating capacity is about 27 terawatts, but that's average consumption, and 100 gigawatts pulsed for just minutes is more achievable than it sounds. Still, it would be one of humanity's largest engineering projects. The light sail must be incredibly light, yet strong enough not to tear under acceleration. It must be reflective enough not to absorb laser light and vaporize. Materials like graphene, just 1 atom thick, have been proposed. Manufacturing sails this large and thin without defects is at the edge of current capabilities. The payload must be miniaturized to an extreme. A gram-scale spacecraft can't carry much. But with modern microelectronics, you could pack sensors, a camera, storage, and a communication system into that mass. The challenge is power. The spacecraft needs energy to operate its instruments and transmitter. Solar panels are one option, but at Alpha Centauri, or our water world, the star's light is far dimmer than our sun's, limiting solar power. Nuclear power at gram scale is difficult. Navigation and targeting are critical. At 20% the speed of light, any particle of dust or gas the spacecraft hits becomes a high-energy collision, potentially destroying it. The spacecraft can't steer, can't avoid obstacles. It's simply fired toward the target and must hope the interstellar medium is clear enough. Statistically, it probably is, but there's risk. Communication from 26 light-years away with a gram-scale transmitter is another challenge. The signal would be incredibly weak. We'd need very large receivers on Earth, probably radio dishes tens or hundreds of meters across, all focused on the signal. Encoding the data efficiently, transmitting it over decades, it would take 26 years for the signal to return, would require careful planning, and there's no slowing down. At 20% the speed of light, the spacecraft will pass through the target system in hours or days, capturing data frantically before racing onward into deep space, never to return. It's a flyby mission, not an orbit or landing. Everything must work perfectly during that brief window. Breakthrough Starshot has not yet been funded at the scale needed to build the laser array, but technology development is ongoing. Miniature spacecraft prototypes have been tested. Laser technologies are advancing. It's conceivable that within a few decades we could launch such a mission to nearby stars. If we did, and if one of those missions was aimed at this water world 26 light-years away, launched in, say, 2050, it would arrive around 2180, fly by the planet, and send back data starting around 2206. People born today might live to see that data return. It's within the realm of possibility. But light sails aren't the only concept for fast interstellar travel. Let's consider another approach that, while more speculative, captures the imagination. Generation ships, entire worlds travelling between the stars. If we can't travel faster than a few % of light speed, then reaching a star system 26 light-years away means a multi-century journey. And for such a journey, you don't send a small probe, you send a world. A generation ship is a spacecraft large enough to sustain a human population for centuries or millennia, a self-sufficient ecosystem travelling through space, arriving at the destination not with the original crew, but with their descendants many generations removed. The concept has appeared in science fiction for decades, but the engineering is grounded in real requirements. Let's think through what such a ship would need. First, population. Too few people and genetic diversity suffers, increasing the risk of inherited diseases over generations. Studies suggest a minimum of several hundred people, ideally thousands, to maintain a healthy gene pool. More people also mean more skills, more redundancy if someone dies or becomes unable to perform their role. Second, space. Psychological studies of confined environments suggest humans need a certain amount of personal space to avoid stress, conflict, mental health issues. A generation ship can't be a cramped tin can. It needs habitable volume, living quarters, communal spaces, areas for recreation, work, agriculture, manufacturing. One design concept is a rotating cylinder, using centrifugal force to create artificial gravity. If the cylinder is large enough and rotates at the right speed, people living on the inner surface experience gravity similar to Earth's. The cylinder might be several kilometers long and a kilometer or more in diameter, with the inner surface landscaped with soil, buildings, parks, creating a habitat that feels less like a spaceship and more like a small valley, with a sky that curves up and over you. Let's talk about the specifics, the unglamorous but essential engineering requirements that make interstellar travel so difficult. Start with energy. To accelerate even a small probe to 10% the speed of light requires enormous energy. The kinetic energy of a 1 kilogram object moving at 10% light speed is about 4.5 times 10 to the 14th joules. That's equivalent to about 107 megatons of TNT, the energy of a large thermonuclear weapon. Now imagine scaling that up to a multi-ton spacecraft or a generation ship weighing millions of tons. The energy requirements become staggering. Where does that energy come from? Chemical energy from rocket fuel? The specific energy of chemical bonds is too low. Hydrogen and oxygen burning together release about 15 million joules per kilogram. To accelerate 1 kilogram to 10% light speed would require about 30,000 kilograms of fuel. And that's without considering the fuel needed to accelerate that fuel. The rocket equation, which governs all reaction-based propulsion, quickly becomes unfavourable at high velocities. Nuclear energy is much denser. Fission of 1 kilogram of uranium releases about 80 trillion joules. Nuclear fusion of 1 kilogram of hydrogen into helium releases about 640 trillion joules. With nuclear energy, fuel mass becomes manageable. At least in theory. But we haven't built interstellar-capable nuclear engines yet. Matter-antimatter annihilation is even more energy-dense, converting mass entirely into energy according to E equals mc squared, releasing 9 times 10 to the 16th joules per kilogram. 1 kilogram of matter meeting 1 kilogram of antimatter would release the energy of a 43 megaton bomb. But we can't make antimatter in significant quantities. Producing even milligrams requires enormous energy and specialized facilities. Storing it without letting it touch matter and annihilate is another unsolved challenge. Now consider navigation. At 10% light speed, you're moving about 30,000 kilometers per second. The distance from Earth to the Moon is about 384,000 kilometers. At this speed, you'd cross that distance in about 13 seconds. You're moving too fast to react to hazards. If there's a rock, a grain of dust in your path, you'll hit it before you can steer away. A grain of sand, 1 milligram, hitting your spacecraft at 10% light speed has kinetic energy equivalent to about 2.3 kilograms of TNT. That's enough to punch through meters of metal. Shielding helps but adds mass, which requires more energy to accelerate, and you can't shield against everything. The interstellar medium, though sparse, contains gas, dust, occasional molecules. Collisions are inevitable. Communication from 26 light-years away is another challenge. Radio signals obey the inverse square law. The strength of the signal decreases with the square of the distance. Doubling the distance quarters the signal strength. At 26 light-years, a signal is incredibly weak. The spacecraft needs a powerful transmitter, a large dish to focus the signal, aiming it precisely at Earth despite travelling at high speed. Earth needs large receivers, long observation times to collect enough signal to decode it, error correction in the data to account for noise and corruption. And there's time. At 10% light speed, a 26 light-year journey takes 260 years. At 1%, it's 2,600 years. Anything on board must last that long. Electronics degrade. Radiation damages computer chips, causing bit flips, errors, eventually failure. Mechanical systems wear out. Lubrication dries up or degrades. Plastics become brittle. Metal fatigues. Without maintenance, systems fail. For a crewed mission, maintenance is possible. For an unmanned probe, everything must be hardened, redundant, designed to survive centuries without intervention. We've never built anything that lasts that long in space. Voyager 1 and 2 are still functioning after 48 years, but they've had no maintenance, and they're starting to fail, instruments shutting down as power dwindles and systems age. Temperature management is critical. In deep space, far from any star, temperatures approach absolute zero, about minus 273 degrees Celsius. Electronics become superconducting, but also brittle. Fluids freeze solid. At the same time, onboard power sources generate heat that must be radiated away. Heat management requires radiators, and radiators are vulnerable to micrometeorite damage. Then there's cost. Building a laser array for breakthrough starshot might cost tens of billions of dollars. Building a generation ship would cost trillions, perhaps tens of trillions, a significant fraction of global GDP sustained over decades of construction. Who funds that? What return on investment justifies it? Scientific knowledge, national prestige, survival of the species by establishing a colony elsewhere? The cost-benefit analysis becomes philosophical, not economic. And we haven't even mentioned the ethical dimensions. Sending people on a generation ship means condemning their descendants to life aboard the ship. Is that ethical? They didn't choose it. You're making a decision that binds not just volunteers but their children, grandchildren, dozens of generations. Is that justified? Even if the goal is noble, unmanned probes avoid that ethical problem but raise others. Is it worth spending trillions to send a robot to a distant world when that money could address problems here on Earth? Poverty, disease, climate change? These are questions without easy answers, and they're as much a part of the challenge as the engineering. Despite all these difficulties, the fact remains. It's not impossible. Physics allows it. Engineering could achieve it. The challenges are immense but not insurmountable. What's required is will, resources and time. If humanity decided collectively that reaching this water world or another star was a priority, we could probably do it within a few centuries of focused effort. Whether we will is a different question. But before we address that, let's consider one more aspect of high-speed travel that makes it even more strange: the way time itself bends at relativistic speeds. Einstein's theory of special relativity, published in 1905, contains a consequence that seems like science fiction but is well-established physics: time dilation. When you move at speeds approaching the speed of light, time for you passes more slowly than for someone at rest. This isn't a mistake in clocks or a perception. Time itself flows differently. At everyday speeds, the effect is negligible. Drive a car at 60 miles per hour for an hour, and you age about 1 nanosecond less than someone standing still. The difference is far too small to measure with ordinary clocks, but at 10% the speed of light, time for the traveller passes about 0.5% slower than for someone at rest. Over a 260-year journey to our water world at that speed, the traveller would experience about 259 years, while Earth experiences 260. A small difference, but measurable. At 50% the speed of light, time dilation becomes significant. Time slows by about 13%. A 52-year journey at that speed would be about 45 years for the traveller. At 90% light speed, time for the traveller passes at about 44% the rate of Earth time. A 29-year journey from Earth's perspective would be about 13 years for the traveller. At 99% light speed, time slows to about 14%. A 26.3-year journey becomes about 3.7 years for the traveller. You could travel to our water world and experience less than 4 years passing, while Earth ages 26 years, not counting acceleration and deceleration time. At 99.9% light speed, close to the speed of light, time dilation is extreme. Earth time passes about 22 times faster than traveller time. A 26-year journey would feel like just over 1 year to the traveller. This creates profound implications. If we could build a spacecraft reaching 99% light speed, a human crew could travel to this water world within their lifetimes. Launch at age 30, arrive at age 34, plus a few years for acceleration and deceleration. But when they sent a message home, it would reach an Earth 26 years older than when they left. Everyone they knew would be a quarter century older. Friends would be middle-aged, elderly, or dead. The world would have changed. Technologies would have advanced. Politics, culture, society, all transformed while the travellers experienced just a few years. If they ever returned, travelling another 26 years from Earth's perspective, but perhaps just a few years of their own time, they'd come back to an Earth 52 years older. They'd be perhaps 40 years old, but everyone else would have aged 52 years. Their younger siblings would be elderly, their parents dead. It would be time travel into the future, one way, irreversible. This is called the twin paradox, though it's not really a paradox once you understand relativity. If one twin travels at high speed to a distant star and returns, they will have aged less than their twin who stayed home. Both experience time normally from their own perspective, but less time passes for the travelling twin. It's been confirmed experimentally using atomic clocks on airplanes and satellites. It's real. For interstellar travellers, this means you can't go home. Not really. You can return to Earth physically, but not to the Earth you left. That Earth, that time, is gone. You're a visitor from the past arriving in the future. There's also length contraction, another relativistic effect. At high speeds, distances appear shorter to the traveller. At 99% light speed, the 26 light years to our water world would appear to the traveller as only about 3.7 light years. Space literally contracts in the direction of motion. This isn't an illusion. From the traveller's reference frame, the distance is actually shorter. They're not moving through 26 light years in 4 years. which would exceed light speed. They're moving through 3.7 light-years in 4 years, which is less than light speed. The space between contracted. Relativity also says you can never reach the speed of light if you have mass. As you accelerate closer to light speed, your mass effectively increases, requiring more and more energy to accelerate further. To reach exactly light speed would require infinite energy, which is impossible. Light itself, photons, can travel at light speed because they have no mass. But anything with mass is forever limited to speeds less than light. This means that no matter how advanced our technology becomes, we can't build a ship that reaches or exceeds light speed, at least not with conventional propulsion. We can get very close, 99.99% or higher, but never quite reach it. The speed of light is a cosmic speed limit, baked into the structure of space-time itself. There are theoretical workarounds involving warping space-time, like the Alcubierre warp drive, but these require exotic matter with negative mass or negative energy density, things we've never observed and might not exist. They're speculative, not proven. So relativity offers a gift and a curse. The gift. If you're willing to leave behind your time, your era, everyone you know, you can travel to distant stars within your lifetime, experiencing the journey as just a few years. The curse, there's no going back. You can visit the future, but never return to your present. For a mission to our water world, if we could reach 99% light speed, a human crew could make the journey in about 4 years of their own time, explore the planet, send back data, and perhaps even return, aging only 8 to 10 years in total, while Earth ages 52 years. It's achievable in principle, though building such a ship is far beyond current capabilities. Would anyone volunteer for such a mission? To leave Earth knowing you'll return to a world where everyone you knew has aged half a century, where your era is history, where you're a relic from the past. Some might. The allure of being the first human to set foot on another world, orbiting another star, the adventure, the place in history, might outweigh the cost. Others would find it too high a price. These are questions we'll face if we ever develop the technology. For now, they remain theoretical, consequences of physics explored in thought experiments and on paper. But the fact that physics allows it, that time dilation makes interstellar travel within a human lifetime possible if we can reach high enough speeds, keeps the dream alive. And perhaps that's what matters most. Not whether we can do it now, but whether we might someday, whether the universe's laws permit it. They do. And that changes everything about how we think about our place in the cosmos. Let's turn now from engineering to philosophy, from what we might do to what it would mean if we did. Imagine the call went out. Quote 3. Who would volunteer? There would be scientists, certainly. Astrobiologists eager to study a potentially habitable planet up close. Geologists wanting to walk on alien ground. Atmospheric scientists ready to breathe the air if it's breathable, or at least study it directly. Astronomers who spent careers observing distant worlds and now have a chance to see one with their own eyes. There would be adventurers, people for whom the frontier is everything, who thrive on exploration, on being first, on going where no one has gone. History is full of such people. Explorers who crossed uncharted oceans, climbed unmapped mountains, ventured into Antarctica's interior, descended to the ocean's deepest trenches. The impulse to explore, to push boundaries, is deeply human. There would be those seeking a fresh start, leaving behind lives they're unhappy with, pasts they want to escape. A multi-century journey means severing all ties with Earth. No communication except time-delayed messages. No possibility of return, at least not to the world you left. For some, that's terrifying. For others, it's liberating. There would be idealists, believers in humanity's destiny to spread beyond Earth, to become a multi-world species, to ensure our survival by not having all our eggs in one planetary basket. They'd see the mission as part of humanity's long-term future, a necessary step even if they personally won't live to see the arrival. There would be families, if it's a generation ship. Parents raising children who will raise children who will raise children, a lineage spanning the journey. What kind of people sign their descendants up for such a fate? Those with profound belief in the mission's importance, willing to impose that belief on their children. It's a heavy moral responsibility. And there would be those motivated by economics or coercion. If Earth's conditions worsened, climate change, resource depletion, political instability, a mission to another world might be framed as escape, salvation. People might go not from desire but desperation. Or governments might select crew not by volunteers but by draft, choosing those with needed skills regardless of preference. History's colonial ventures often involve such dynamics, willing explorers mixed with transported labourers, convicts, or indentured servants. We'd like to think space exploration would be different, but history suggests optimism should be tempered. Whoever goes, they'd need training, years of it. Learning ship systems, maintenance, life support, navigation, medicine, agriculture, manufacturing, all the skills needed to keep a small society functioning. Psychological evaluation too, screening for those who can handle confinement, isolation, the mental challenges of knowing you'll never return. They'd likely undergo genetic screening, ensuring diversity, minimising heritable diseases. For a generation ship, population genetics matters. Too much inbreeding and harmful recessive traits accumulate. Enough diversity, and the population remains healthy over time. There would be cultural preservation efforts. Libraries, databases, storing human knowledge, art, music, literature. Not just practical knowledge, but cultural heritage. The crew would carry Earth's culture with them, becoming a new branch of humanity growing under a different sun. And there would be rituals, ceremonies, marking the departure. A final goodbye to Earth, to everyone staying behind. Families saying farewell to crew members, knowing they'll never see them again. Not even via video once the ship is far enough that communication lag becomes years, decades. The psychological weight of that separation would be enormous. Launch day would be momentous. Billions watching as the ship departs, accelerates, eventually vanishes into the darkness between stars. For those aboard, watching Earth shrink to a blue dot, then disappear entirely into the starfield, indistinguishable from other points of light. That moment when Earth is no longer visible, when you're truly alone in the void, would change you. Decades would pass. Crew living in artificial gravity, tending gardens, raising children, teaching them about Earth, about the destination, about the purpose of the journey. Maintaining discipline, purpose, hope, dealing with failures, accidents, deaths, births too, celebrations, marriages, the continuation of life even in metal and emptiness. And finally, centuries later, arrival, the water world growing from a star to a disk to a globe filling the sky. The first orbit, sensors mapping the surface, confirming what spectroscopy suggested. Oceans, land, clouds, weather. The first landing, if they dare, setting foot on soil never touched by anything from Earth, breathing air under an alien sky, looking up at a red sun. What would that moment be like? The culmination of centuries of travel, dozens of generations of waiting. Finally arriving, would it feel triumphant, anticlimactic, terrifying, sacred? Would they kneel and weep, or simply get to work setting up base camp, beginning the long process of exploration and perhaps colonization? These are questions we can only imagine answers to, but they're worth imagining, because in thinking about who would go and why, we reveal something about ourselves, about what drives humanity, what we value, what we're willing to sacrifice for knowledge, for survival, for the continuation of our species beyond our birth world. And if anyone did go, what would they leave behind? Let's think about Earth, waiting, watching, hoping for messages from the distant voyagers. While a crew journeys to a water world 26 light-years away, life on Earth continues, Decades pass. Generations grow up, grow old, die. The mission that was headline news at launch becomes history, then memory, then something most people have only read about in old articles. Earth would receive messages periodically, early on while the ship is still relatively close, perhaps yearly. The crew sends updates, systems functioning, journey progressing, small events aboard ship. Earth responds with news, encouragement, technical advice if systems malfunction. The exchange is real, meaningful, though each message takes years to send and receive. As distance grows, communication slows. 10 light-years out, a message takes 10 years to reach Earth. A reply takes 10 more years to return, 20-year conversations. By the time a question is answered, the question may no longer be relevant. The crew might have solved the problem themselves, or the situation changed entirely. Communication becomes less dialogue and more monologue, shouting into darkness and hoping someone eventually hears. At 26 light-years, when the ship finally arrives, any message they send, "We're here, we've arrived," takes 26 years to reach Earth. The crew experiences the arrival moment immediately, but Earth won't know for a generation. A child born on Earth the day the ship arrives will be 26 years old before Earth receives the news. What would Earth do with those messages? Perhaps they're studied carefully, every word analysed. Perhaps there are dedicated listening stations, teams of people monitoring for signals ready to respond. Perhaps the mission becomes a cultural touchstone, something every generation learns about, follows, invests emotionally in. Or perhaps, over time, interest wanes. A century into the journey, few people alive remember the launch. The mission is ancient history, something grandparents talk about but current generations don't particularly care about. Funding for the listening stations might decline. Political priorities shift. Wars, economic crises, climate events, all draw attention and resources. The mission becomes a footnote, a curiosity, maintained by a dedicated few, but largely forgotten by broader society. This happened with the Voyager probes in a small way. They're still out there, still sending data. But most people don't think about them. They were major news in the 1970s and 80s, their discoveries front-page headlines. Now, they're background noise, still scientifically valuable but not culturally prominent. A multi-century interstellar mission would face the same cultural erosion, magnified by time. But imagine the moment when a message finally arrives. 260 years after launch, assuming 10% light speed and direct communication, Earth receives, "We're here, we've arrived, the planet is real, water is confirmed, we're beginning surface exploration." That message, travelling 26 years to reach us, delivered to a world where everyone who launched the mission is centuries dead. Would it reignite interest? Would it be major news, celebrated globally, a unifying human achievement? Or would it be a curiosity, interesting but not life-changing for people whose daily concerns are immediate, local, personal? The data would be scientifically invaluable. High-resolution images of the planet, detailed atmospheric composition, perhaps samples if they landed, surface geology, weather patterns, measurements of radiation, temperature, magnetic field strength. All the information Webb and other telescopes can't provide from 26 light-years away. It would revolutionize exoplanet science, giving us a template for understanding similar worlds. If they found life, even just microbes, it would be the most significant discovery in human history. Proof that life exists beyond Earth, that we're not alone, that biology is a cosmic phenomenon, not a terrestrial accident. The philosophical implications would be staggering, reshaping religion, philosophy, our understanding of our place in the universe. And Earth would respond, sending more messages, asking questions, planning follow-up missions perhaps. But by the time Earth's questions reached the crew, another 26 years would have passed. The crew, if still alive, if the mission succeeded, would be old, perhaps near the end of their lives. Their answers would take another 26 years to return. Conversations spanning a century, questions posed by people long dead, answered for audiences not yet born. There's a melancholy to this temporal dislocation. The connection between Earth and the mission becomes tenuous, strained by time and distance. Each message is a voice from the past. Each response comes to people who weren't there when the question was asked. It's communication, but not the kind we're used to, not real-time dialogue, not even conversation in any normal sense. It's messages in bottles, cast into the ocean of time, eventually washing ashore on distant beaches. Yet it would persist, as long as anyone cared enough to keep listening. And there's something beautiful in that persistence, in humanity maintaining a connection across the void, across decades and centuries, talking to itself across the stars. From Earth's perspective, the mission would be a long arc, bending from present into future, a thread connecting generations, a story unfolding so slowly that no individual sees the whole narrative, only their chapter. We launch the ship. Our grandchildren's grandchildren receive the first data. Their grandchildren's grandchildren receive the complete story, and each generation adds its part, maintaining the mission, interpreting the data, passing the knowledge forward. This is the timescale on which interstellar exploration operates. Not human lifetimes, but human lineages. Not individual achievement, but civilizational continuity. It requires thinking beyond ourselves, caring about outcomes we'll never see, investing in futures we won't inhabit. That's hard, but perhaps necessary, for a species that wants to reach beyond its birth world. Let's think even larger now, stepping back from individual missions and considering the full scope of time ahead. Humanity, in our current form, Homo sapiens, has existed for about 300,000 years. Civilization, agriculture, cities, writing has existed for perhaps 10,000 years. Industrial technology, the machinery and infrastructure that defines modern life, is about 250 years old. Space travel is about 70 years old. The entire history of space exploration, from Sputnik in 1957 to today, fits within a single human lifetime. We are breathtakingly young as a technological species. And yet we're already contemplating interstellar travel, already detecting planets light years away, already imagining how to reach them. That's remarkable, but it's also worth contextualizing. The Earth is 4.5 billion years old. Life appeared about 3.8 billion years ago. For most of that time, life was simple, single-celled, invisible to the naked eye. Complex life, animals, plants, emerged only in the last 600 million years. Intelligent life, humans, only in the last few 100,000. Technological civilization, only in the last 10,000. In Earth's 4.5 billion year history, our entire species exists in the last blink of an eye. And our technological phase, the part where we've had the capability to detect exoplanets and contemplate reaching them, is a tiny fraction of a blink. Looking forward, the future is almost incomprehensibly long. The sun will keep shining for another 5 billion years. The red dwarf star our water world orbits will shine for trillions of years. The universe itself will continue for at least trillions of years, perhaps forever, depending on cosmological details. Humanity has time, enormous, staggering amounts of time. If we survive, if we don't destroy ourselves or get wiped out by some catastrophe, we have billions of years ahead. That's time enough to spread across the galaxy, to reach not just nearby stars but distant ones, to settle thousands or millions of worlds, to become a truly spacefaring species. But survival is not guaranteed. Civilizations are fragile. Ours is facing climate change, environmental degradation, nuclear weapons, pandemics, political instability. All threats that could set us back or end us. Past civilizations on Earth have collapsed. The Roman Empire fell. The Bronze Age civilizations of the Mediterranean collapsed. The Maya civilization in Central America collapsed. These weren't global catastrophes, but they show that even powerful, advanced societies can fail. For the first time in history, we have the capability to render ourselves extinct. Nuclear war could kill billions and make much of the planet uninhabitable. Climate change could trigger cascading failures in ecosystems and agriculture. A pandemic worse than COVID-19 could emerge. An asteroid impact, while rare, is possible. Any of these could end our story before we've barely begun. But if we navigate these dangers, if we make it through the next few centuries with our civilization intact and our planet still habitable, the long-term future is open. We could become the species that spread Earth's biology across the galaxy. Every tree, every animal, every microbe that makes the journey to another world would be descended from Earth life. We could seed the galaxy with ecosystems, create new biospheres on barren planets, terraform worlds to be more Earth-like, or settle worlds like this water planet that are already habitable. We could encounter other intelligent life, and if we do, it would redefine existence. We'd learn we're not alone, that intelligence emerges elsewhere, that the universe is full of minds and civilizations, or we might find we're alone, that despite billions of stars and planets, we're the only ones here, at least in our galaxy. That would be equally profound, suggesting intelligence is rare, precious, fragile, and making our survival even more cosmically significant. Either way, the decisions we make now, in this century, in this generation, matter immensely. We're at a pivot point. We could go either way, extinction or expansion, collapse or survival. The discovery of water on a world 26 light-years away is part of this story, a step toward understanding our cosmic neighbourhood, toward finding places we might one day go, toward ensuring humanity's future isn't tied solely to Earth. Interstellar travel might seem far off, speculative, a dream for future generations, and it is. We won't see it in our lifetimes. Probably not in our grandchildren's lifetimes, but someone will, if we keep progressing, keep building, keep reaching. The James Webb Space Telescope detecting water on that distant world is a step on that path. So is every exoplanet we discover, every atmospheric molecule we detect, every technological advance in propulsion and energy and life support. We're laying groundwork. We're learning what's out there, where we might go, what we'd need to get there. We're building the knowledge base that future generations will use to actually make the journey. That's our role in this long story. The early chapters, the setup, the foundation. And in that context, our individual lives, as brief as they are, connect to something larger. We're part of a species with potentially billions of years ahead. We're part of a lineage that might one day walk on 100 worlds under 100 different stars. We're the ancestors that future humans will look back on, the generation that first saw these distant worlds, first understood what was out there, first dreamed of reaching them. There's a weight to that, but also a lightness. Our individual struggles matter less in cosmic context, but our collective journey matters more. We're participants in something vast, something that extends far beyond our tiny window of existence, something beautiful and improbable and worth preserving. This is what the discovery of water on that distant world reminds us of. Not just that water exists out there, but that we're capable of finding it, of understanding it, and perhaps, one day, of reaching it. Let's allow ourselves to feel the wonder of that. There's a photograph, taken by Voyager 1 in 1990 at Carl Sagan's request, showing Earth from just beyond Neptune. Earth appears as a tiny speck, less than a pixel, a pale blue dot suspended in a sunbeam. Sagan wrote about this image, reflecting on how it shows our planet as it truly is, small, fragile, alone in the cosmos. But there's another way to see that image, and images like it, not as diminishment, but as elevation. Look how far we've come. To build a spacecraft that could travel billions of miles, turn around and photograph home. Look what we're capable of, that we can send our eyes and instruments across the solar system, across light years, detecting worlds we'll never physically touch, understanding them through mathematics and physics and ingenuity. The discovery of water on a planet 26 light-years away is an achievement of that same kind. We built a telescope, sent it 1,000,000 miles from Earth, cooled it to almost absolute zero, pointed it at a distant star, measured the infinitesimal dimming as a planet passed in front, analysed the spectrum of that filtered light, and said with confidence, "There is water there. That's extraordinary." It's easy to become numb to such achievements, to accept them as routine, to scroll past the news without pausing to feel the weight of it. But pause for a moment. We detected the presence of specific molecules in an atmosphere 246 trillion miles away. We did that. Humanity did that. This ability to understand the distant universe, to reach out with our minds and instruments, and comprehend what exists far beyond our physical reach, is perhaps our species' greatest achievement. Not because it's useful, though it might be one day, but because it expands our conception of what's possible, who we are, where we fit. For most of human history, the sky was mystery. The stars were points of light, beautiful but incomprehensible. We invented stories about them, saw patterns, constellations, gods and heroes. But we didn't know what they were. We didn't know they were suns like ours. We didn't know planets existed around them. We didn't know we could detect water on those planets. Now we know, and knowing changes us. It changes how we see ourselves, our world, our future. We're not bound to Earth, not cosmically. We're a species that can look outward, understand outward, and potentially one day travel outward. The water world 26 light-years away might be lifeless. It might be hostile, radiation-scorched, uninhabitable despite its water. Or it might be teeming with life, oceans full of organisms we can't imagine. We don't know yet, but we will, eventually. Webb will keep observing, other telescopes will follow, our understanding will deepen, and perhaps centuries from now someone will go there and see for themselves. That future person, standing on that alien shore, looking up at a red sun, will be there because we, today, discovered water. Because we built the telescopes. Because we asked the questions. Because we didn't accept Earth as the boundary of human experience but reached further. Always further, driven by curiosity and wonder. This is why the discovery matters. Not just for the scientific data, though that's valuable. Not just for the possibility of finding life, though that would be transformative. But for what it represents: human capability, human persistence, human refusal to accept limits on what we can know and where we can go. There's something deeply hopeful in that. In a world often dominated by division, by short-term thinking, by failures to cooperate on global challenges, the scientific community keeps working, keeps building, keeps discovering. The James Webb Space Telescope is a product of international collaboration, thousands of people across many countries working together toward a common goal. It's a glimpse of what we can achieve when we cooperate, when we think long-term, when we prioritise knowledge and exploration over immediate gain. And the knowledge we gain transforms us. Every exoplanet discovered changes our understanding of planetary formation, of what kinds of worlds exist, of how common or rare Earth-like conditions might be. Every atmospheric detection teaches us about chemistry, climate, the interplay of geology and atmosphere and star. This knowledge feeds back into understanding our own world. Climate science relies on understanding how atmospheres work, how greenhouse gases trap heat, how feedbacks amplify or dampen changes. Studying other planets gives us comparison points, natural experiments in planetary climate. Venus shows us runaway greenhouse effect. Mars shows us atmospheric loss. This water world, if we learn more about it, might show us a climate stable over billions of years, or one that changed catastrophically, or one that cycles between states. Each example enriches our understanding. But beyond practical knowledge, there's the expansion of imagination. a generation growing up knowing that water worlds exist light years away, that we can detect them, that we might one day reach them, grows up with a larger sense of possibility. They're less likely to see Earth as all there is, less likely to accept limits, more likely to dream big, to think long-term, to value science and exploration. This cultural shift, subtle but significant, is part of why such discoveries matter. They change what we think is possible. They change what we aspire to. They change in small ways who we are as a species. And there's beauty in the pursuit itself, in the journey toward knowledge, regardless of destination. The process of building Webb, of planning observations, of analysing data, of debating interpretations, of gradually constructing an understanding of distant worlds is beautiful. It's humans at our best, curious, rigorous, cooperative, persistent. Let's bring this home now to the night sky above us, to the connection between these distant worlds and our own experience. Go outside on a clear night, away from city lights if you can. Look up. The sky is full of stars, thousands visible to the naked eye, billions if you had perfect vision and no atmosphere to dim them. Each point of light is a sun, many of them larger and brighter than ours, some smaller and dimmer, all of them shining across the years and decades and centuries, their light travelling to reach your eyes. Somewhere among those stars, though you'd need a telescope to spot it, is the red dwarf hosting our water world. It's there, real, existing right now, 26 light-years away. Around it, a planet orbits, completing its dance every few days, tidally locked, one face always sunlit, the other always dark, with water vapour in its atmosphere. That water is there whether you think about it or not, whether you know about it or not. The universe doesn't require our attention to exist. Stars shine whether we watch them or ignore them. Planets orbit whether we detect them or remain ignorant. Life, if it exists out there, lives and dies without caring if we know. But knowing changes us. Standing under that sky, aware that among those stars are worlds with water, with atmospheres with the potential for life, changes how the sky feels. It's no longer just pretty lights, no longer just a backdrop. It's a neighbourhood, a region of space containing places, destinations, worlds we might one day visit or at least understand more deeply. This shift in perspective is what astronomy offers. It connects the abstract to the concrete, the distant to the immediate. Those aren't just stars. They're suns. Those suns have planets. Those planets have geology, weather, chemistry. Some might have life. Some might have civilizations looking back at us, wondering if anyone is here. The night sky becomes a map, a vista of possibilities, a reminder of scale both humbling and inspiring. Humbling because we're so small, one planet among trillions, one species among possibly countless others. Inspiring because we're capable of understanding this vastness, of reaching out across it with our instruments and minds, of contemplating our place within it. There's a particular star, visible from the northern hemisphere in the constellation Cygnus, called Kepler 452. It's about 1400 light-years away, hosts a planet called Kepler 452b, sometimes called Earth's cousin, a rocky world in its star's habitable zone. You can see that star with binoculars, a dim point of light, and know that around it orbits a world roughly similar to Earth in size and location. There's another star visible from southern latitudes called Proxima Centauri. It's the nearest star to our Sun, just over 4 light-years away, and it has planets. One of them, Proxima Centauri b, is roughly Earth-sized and in the habitable zone. You can see Proxima with a decent telescope, a faint red dot, and know that just 4.2 light-years away, closer than almost any other star, there's a world that might possibly be habitable. And now there's this water world, 26 light-years away, orbiting its red dwarf star. You can't see it with your eyes, probably can't see the star without a telescope, but it's there. Its water is there. Its atmosphere is there. Reality doesn't wait for our ability to perceive it. These stars, these worlds, they're all part of the same galaxy we live in, the Milky Way. On a dark night, far from light pollution, you can see the Milky Way itself, a band of light across the sky, the combined glow of billions of stars in the galaxy's disk. Somewhere in that band are stars with water worlds, with habitable planets, possibly with life. We just don't know which ones yet. But we're learning. Every year, more exoplanets discovered. Every year, more atmospheric detections. Every year, our census of the galaxy's worlds grows more complete. We're mapping the neighbourhood, finding out who our neighbours are, what their properties are, which ones we might want to visit. And this mapping isn't just academic, it's preparatory. We're doing reconnaissance for a future where humanity might actually travel to these places. We're identifying targets, understanding conditions, learning what we'd encounter if we went there. Future generations will look back on our era as the time when humanity first truly saw the galaxy's planets, first understood what was out there, first made the detailed observations that would guide later exploration. In that sense, every discovery, including this water world, is a waypoint, a marker on a path leading outward. We're building the roadmap star by star, planet by planet. Standing under the night sky with this knowledge, the stars feel closer. Not physically, they're still light years away, still impossibly distant by human standards. But conceptually, intellectually, emotionally, they feel reachable. They're no longer just lights, but destinations. They're no longer just distant, but connected to us through understanding and possibility. And if you ever feel small, looking up at that vastness, remember this. You're part of the species that learned to measure those distances, to detect those planets, to understand that water exists out there. You're part of a lineage that built telescopes capable of seeing across 26 light years and reading the chemical composition of an atmosphere. That's not small. That's extraordinary. The universe is vast, yes, but we're capable of comprehending that vastness, of finding our place within it, of reaching toward it with our tools and dreams. We're tiny, but we're also magnificent. We're brief, but we're also connected to something that extends billions of years into the past and potentially billions more into the future. Hold that thought as we come to the end of this gentle journey. Let's bring it all together. Thank you for staying with me through this long drift among the stars. We've travelled together across 2.5 hours, from the moment James Webb detected water vapour on a distant world, through the science of how we made that discovery, into the challenges of reaching such a place, and finally to the larger questions of what it all means. Thank you for giving me your time, your attention, your late night hours. It means more than you might know. Let's think back on the journey we've taken. We started with spectroscopy, with light passing through an alien atmosphere 26 years ago, carrying information that eventually reached our telescope. We explored what that water world might be like, a rocky planet orbiting a red dwarf sun, possibly with oceans under a red sky, with weather and chemistry and perhaps even life. We considered the engineering challenges of reaching it, the enormous energies required, the centuries of travel time, the time dilation effects that would make the journey strange and lonely. And we contemplated why it matters, why discovering such worlds expands who we are and what we might become. So where does that leave us? What's the answer to the implicit question we've been exploring all night? Could we reach this water world, and should we try? The answer, as honestly as I can give it, is this. We could reach it eventually if we survive long enough and commit the resources. The physics allows it. The engineering is difficult, but not impossible. Whether we should try is a question each generation will answer for themselves, weighing the costs against the benefits, the practical against the idealistic, the immediate needs of Earth against the long-term survival and expansion of our species. There's no one right answer, but the fact that we can ask the question, that we've reached a point where interstellar travel is genuinely on the table as a real possibility rather than pure fantasy, is itself remarkable. If you enjoyed this slow drift through cosmic questions, a like would mean the world, and subscribing helps others find these quiet explorations. And if you'd like to share where you're watching from, or what this discovery makes you think about, the comments are always open. I read them all, and I'm grateful for every thought you share. For those who've been here before, who return video after video to explore the universe with me, thank you. You're the reason I keep making these. So wherever you are in the world, wherever you're lying or sitting or resting as you listen to this, I hope your mind feels a little more settled, your thoughts a little quieter, your body a little heavier, and more ready for rest. I hope the day's anxieties have faded, replaced by the gentle awareness that you're part of something vast, that above you, even if you can't see them, stars are shining, and around some of those stars, worlds are waiting, with water in their skies and mysteries we're only beginning to uncover. I hope your breathing has slowed naturally over these 2.5 hours. I hope your shoulders have dropped, your jaw unclenched, your muscles relaxed into whatever surface supports you. I hope you feel the weight of your own body, the warmth of the blankets or the air, the softness of where you rest. Look up if you can. Imagine looking up at the night sky above us. Imagine all those stars, each one a sun, many of them with planets, some of those planets with water. Picture the Milky Way stretching across the darkness, billions of suns in our galaxy alone. And know that 26 light years away, barely any distance at all in that grand cosmic scheme, there's a world where water exists, where an atmosphere filters light through vapour, where chemistry happens, where the same molecules that make up your body exist in alien air under an alien sun. That world is real, existing right now, whether we think about it or not, and we found it. We, tiny humans on one small planet, reached across the void with our cleverness and our curiosity and said, "There you are, we see you." There's something profoundly peaceful in that knowledge. We're not alone in the universe, not even if we never find life. Water is out there. Worlds are out there. The universe is full of places, full of complexity, full of chemistry and physics unfolding in countless variations. And we're part of it, connected to it all, made of the same atoms, governed by the same laws, looking outward and seeing ourselves reflected in distant planetary atmospheres. Sleep well knowing this. Dream of red suns and alien oceans, of water vapour rising into strange skies, of distances measured in light years slowly shrinking as our understanding and capability grow. Dream of a future where this water world isn't just a point of light in a telescope, but a place, a destination, maybe even a home. And when you wake, the stars will still be there, the water world will still be there, the universe will continue its patient, majestic unfolding, and we'll still be here, still learning, still reaching, still adding our small chapter to the vast story of existence. Good night.